All right, let's talk about something you are using this very second, but maybe don't think about too much: electricity. I mean, it's everywhere, right? Powering our lives. But what is it, really? Let's pull back the curtain and take a look. You know that feeling, right? You reach for a doorknob and zap, you get that little shock. Or you're taking off a sweater in the dark and hear it crackle and see tiny sparks. Well, that little jolt isn't just a random annoyance. It's actually a clue, a tiny peek into one of the most powerful forces in the universe. Because that exact same force, just on a slightly bigger scale, creates this, a massive bolt of lightning. Yeah, believe it or not, the same fundamental principle connects the awesome power of a thunderstorm to the quiet crackle of your laundry. And it's the very same magic that lets a plastic comb, after a quick run through your hair, suddenly pick up little bits of paper, like a magnet. So what is it? What's the invisible thread connecting all these things? Well, that hidden world has a name: static electricity. It's this invisible charge that can build up on things, just kind of hanging out, waiting for a chance to jump. So let's dig into how it actually works. To really get static electricity, we have to start with the basic idea of charge. And it turns out, charge isn't just one thing. Nope, it has two different faces, and they follow one simple, fundamental rule that explains everything. Okay, let's try a little thought experiment. You take a normal plastic straw, and you just rub it with a piece of paper. That little bit of friction is all it takes to load that straw up with an electric charge. Now here's where it gets cool. If you charge up a second straw in the exact same way and you bring it close to the first one, they literally push each other away. You can feel it. They repel. But what if we switch things up? Instead of another straw, let's take a glass bottle and rub it with, say, a piece of silk to give it a charge. Now, when we bring that bottle near our straw, they pull towards each other. They attract. And right there, that tells us something huge. There have to be at least two different kinds of charge. And just like that, those simple little experiments reveal the single most important rule in all of electricity. It's so simple, but so powerful. Charges that are the same push each other away, and charges that are different pull each other together. Opposites attract, likes repel. That's it. That's the core of the whole thing. So what are these charges, really? Well, it was actually Benjamin Franklin who gave them the names we use today: positive and negative. But here's the real mind bender. When you rub two things together, you aren't creating charge out of thin air. All you're doing is moving these teeny tiny negative particles, we call them electrons, from one object to the other. So the thing that loses electrons is left with more positives, right? So it becomes positively charged. And the thing that gains all those extra electrons becomes negatively charged. It's all just a transfer. Okay, so we know they push and pull, but the next logical question is, how much? How strong is that invisible force? Can we actually put a number on it? Turns out, yes, we can. And for that, we have to thank this guy, French physicist Charles-Augustin de Coulomb. Back in the 1780s, he did some incredibly clever experiments to finally measure this force. He wrapped up everything he found into what we now call Coulomb's law. And okay, yeah, the official wording sounds a little dense and academic, but the idea behind it is actually super straightforward. Let's just break it down. It really just boils down to two simple things. First, the more charge you have, the stronger the force. Makes sense, right? And second, the farther apart the charges get, the weaker the force gets. More charge, more force. More distance, less force. See? Super elegant and totally predictable. So far, everything we've talked about is static electricity. You know, charges that build up and just sit there until they zap something. But the electricity that's actually powering your screen right now, that's not static at all. That's all about getting those charges to move. So to get charges to move, they need a reason. They need a push. And in electricity, we call that push potential difference. But you probably know it by a much more common name: voltage. Just think of it like electrical pressure. The higher the voltage, the harder the push. Honestly, the best way to picture this is to think about water flowing through a pipe. It's a perfect analogy. The voltage is like the water pressure pushing the water along. The wire is the pipe that contains it all. And the amount of water actually flowing through the pipe, well, that's our next piece of the puzzle. That flow, the actual movement of charge, is what we call electric current, and we measure it in amps, or amps for short. So just like you'd measure water in, say, liters per second, we measure current by how much charge is flowing past a point in the wire every second.
Simple, right? Voltage is the push, current is the flow.
Now, we keep talking about charge. The official scientific unit for it is the coulomb, named after our guy Charles. But what does 1 coulomb of charge actually mean? Like on a particle level? Well, you might want to brace yourself, because the answer is kind of staggering.
That is the number of electrons it takes to make up 1 single coulomb of negative charge. I mean, just look at it. It's 6.25 quintillion. It's a number so big our brains can't even really comprehend it. And it just goes to show you how unbelievably tiny these little particles are.
And here is where it all clicks together. Remember how 1 amp of current is 1 coulomb of charge flowing per second? Well, that means that in a normal wire carrying just 1 measly amp, that ridiculous number, over 6 quintillion electrons are streaming past any single point every single second. It's an invisible, perfectly controlled stampede happening inside a piece of metal. So seriously, the next time you flip on a light or plug something in, just stop for a second and picture that. You're not just closing a circuit. You are commanding a river of trillions upon trillions of electrons to flow on demand to do your bidding. When you think about it like that, it's pretty incredible, isn't it?